Okay, today I would like to talk about geometry Hardy inequalities on star-shaped sets. This work was joint work with Professor Rozhansky and Dr. Suragan. This work was devoted to deriving geometry Hardy inequalities on star-shaped sets in Carnot groups, with some examples on Heisenberg group angle groups. Also, we established geometry Hardy inequalities on half space of general vector fields with examples on Gaussian plane. First, I will give a very short, brief introduction of settings. The first setting is sub-Riemann manifold. MB is smooth manifold with dimension n with given familiar vector fields, whereas a peak n is smaller than dimension n, and defined on manifold M and satisfying Hermander condition. Then we have sub-Riemann metric in associated space spanned by these vector fields. And this triple called sub-Riemann manifold. Note that unlike for Carnot groups, it's not possible to define dilations, translations, or homogeneous norm, and the distance in the setting of this sub-Riemann manifold. Then we can define the operator called sum of the squares of vector fields in this following form, and we also have horizontal gradient from these vector fields. One of the important examples of sum-Riemann manifold is a Gaussian plane. Gaussian plane is space of R2 with vector fields in this following form. Next setting is the Carnot groups, or we call it stratified Lie groups with dilation structure, delta omega and Jacobian generators, where n is dimension of first stratum of this group. Then Q is a homogeneous dimension. For more details, we refer to recent book of Rozhansky and Suragan on Hardy inequalities on homogeneous groups. One of the important examples in Carnot groups in step 2 is a Heisenberg group, and the Heisenberg group has a left invariant vector fields which spanned by these two vector fields and with commutator in this following form. Also, we give example in step 3 stratified groups, which is an angle group. Angle group is with vector fields x1 and x2, and with commutator we can obtain x3 and x4. Now we can give a definition of star-shapedness. It is due to work of Danieli and Grafova. They introduced it in the work of here in 1995. Let be omega set of Carnot groups with containing identity E. Then omega is star-shaped with respect to this identity. If for every x in the boundary one has this inequality, this is just dot products, whereas Z is the vector fields, and it's Riemann autonormal to boundary. We call it strictly star-shaped with respect to identity if it's strictly bigger than 0. Where the vector field has this following form, and if we open this dot product, it has this following form. It's very easy. Then by this definition, we can introduce or establish geometry Hardy inequalities. Okay, again, the omega is a star-shaped set for every any number omega, gamma, and for p bigger than 1, we have this kind of Hardy inequality and LP case. And here we have weight that by choosing n we can generate most of the terms. And as example, in Heisenberg and Engel groups, we give this following Hardy inequalities. First, H star is star-shaped set in Heisenberg group, and E star is Engel group. For Engel group, then we can define this kind of Hardy inequality, which can be recovered from 4, and the inequality 6. Here we have an extra term, but in Heisenberg group we don't have.
Attends, j'écoute là.
What?
Pardon.
Okay. So then also we can obtain Hardy inequality on Hull spaces of subriemann manifold. First, we just define subriemann manifold in this following form. Again, the n is Riemann auto unit normal to boundary. Also, we define the distance to boundary in this following form. Then for every gamma n for p bigger than 1, we have this kind of Hardy inequality. This inequality was proved in the case of Carnot groups in the work on number 3. And here we give example in Grothian plane, where we have this kind of Hardy inequality in Grothian plane. It's interesting that when p equal 2, this last term disappears. So our references, and this work was accepted to the Journal of Convex Analysis. So thank you for your attention. So if you have any question, please ask.
Thank you very much for this nice presentation. Marius, please.
I'm curious if there is some possibility of Relic type inequalities, but maybe they cannot even be defined. I'm not sure of this.
I have tried to do it, but when we put this kind of weight, they disappear. It will be same as general case.
Okay.
It will be like too much terms, but I can try again. Maybe that time I was like know a little bit, so maybe I can try for get Relic inequalities for this kind of weights.
Yes, okay. And maybe if you put some weight in the side in which you have the, let's say, the gradient, or how is it called? Is it possible? So instead of having in the left-hand side just nabla h, if you also have a weight.
Yes, yeah, it will be same.
Euclidean case.
Yeah, it will get Euclidean case because of we will choose this autonormal like 0, 0, 1. We can get Euclidean case.
Good, thank you very much.
So are there any other questions? If not, then thanks again. Thank you very much.
Thank you.
And then it's our next Blitz speaker's turn, Dr. Vishwesh Kumar from Ghent University.
Just sitting. Wait a minute.
Before I announce the wrong title again.
No, it's the same.
I'll just hand over to you, please.
I don't know. Can you see my screen now, David?
Yes.
Okay, thank you. So can I start?
Yes, please.
Okay. So today I will talk about or briefly give update our activity here with my colleague Duan Cardona, who is also one of the organizers and our leader Mikhail Rozhansky and our postdoc here Nihat Tukumadamtev about the LP-LQ boundedness of pseudo-differential operator on smooth manifold and the application of the obtained result to the nonlinear PDE. So the main aim of this poster is to generalize the work of Hormander on boundedness of LP-LQ boundedness of Fourier multiplier or more generally pseudo-differential operator on manifold using the Fourier analysis developed by Nihat, last author of this paper, which they call non-harmonic Fourier analysis. So, and this the LP-LQ boundedness pseudo-differential operator or in particular multiplier was originated in the seminal paper of Hormander in 1960, which appeared in Acta Math, and is now very famous. And recently, Michael Rozhansky and Ruan Akiljano, they started this program to extend those results to different settings. So they extend it to compact groups, compact quantum groups, and also very recently on compact locally compact groups where they use fundamental algebra techniques. So the aim of this poster is to generalize in the similar line of research, but using the non-harmonic analysis. So what is the non-harmonic analysis or non-harmonic Fourier analysis? So we consider a pseudo-differential operator L, which can be elliptic or non-self-adjoint also, and we put some boundary condition so that the eigenfunctions. And we assume that that has a discrete spectrum and eigenfunction satisfies some boundary condition. And using this eigenfunction expansion, we define the Fourier analysis similar to Euclidean space. If you consider the Laplacian, and of course their spectrum is not discrete, but it is similar. You can say on the you can assume harmonic oscillator on Rn, and then harmonic oscillator can serve a example for such kind of operators. So we define the Fourier transform, and then in these two papers, which was kind of origin of this kind of analysis, these two, one is this one, and then the other one this, where they discuss pseudo-differential calculus in these settings, and they obtained Planck-Charel formula for this Fourier analysis, and they developed Hausdorff-Young inequality, another fundamental inequality in this setting. Okay, so using the inverse Fourier transform of L Fourier transform, we define the pseudo-differential operator, and by introducing the symbols M, and then using the symbol M, we define the pseudo multiplier in like this, and then now we will discuss theorem for the LP boundedness of the pseudo multiplier. So our first result is LP boundedness of the pseudo multiplier, which says if you consider a pseudo multiplier, and if the symbol of the pseudo multiplier satisfies this Hormander-Millin type of condition, then it can be extended to a boundary linear operator for all LP between LP or P between 1 to infinity. For this condition, we need some extra assumption that the eigenfunction of the operator L, which we consider is of polynomial growth, and the second, it satisfies wild eigenvalue type of counting formula. The second result we have here is LP-LQ boundedness of Fourier multiplier. So if the symbol of the Fourier multiplier satisfies this condition, which is finite, then it can be extended to from LP to LQ between this range. And we need these two conditions because of the because of the possibility of non-self-adjointness of operator L. So this is our final and main result, you can say, for pseudo-differential operator. So in this case, we need to assume a compact manifold, M is compact. It can be with or without boundary, and if the symbol satisfies this condition, then it can be extended to the LP to LQ with this range. And as a consequence of this theorem, we study the local well-posedness or Cauchy problem So we consider three type of basically Cauchy problem. One is first wave equation, then parabolic type of heat equation. So these are the application here we consider, and we obtain well-posedness of this using the result we obtain here for Fourier multiplier and pseudo differential operator. So here are some references. So this is the recent paper which I was talking about on the LPLQ multiplier of the locally compact groups, and this is the paper where all the results appear. It's still in archive, it's not appearing in general, and the symbol of Hormander, and these two papers are where the non-harmonic analysis related with one model operator L has been developed for the manifold, and that's all. Thank you.
Thank you very much, Vishwesh, for this interesting presentation. Are there any questions? Nobody?
So I will stop sharing now.
No, maybe I've got a short question. So since you said this was in the line of the program started by Michael and Rawan originally, so what might the next step be?
There are several directions. Like now I am working on some like Professor Anker told symmetric spaces. So I'm trying to like do the similar kind of extension in LPLQ, because for the symmetric spaces till now LP boundedness was proved by Professor Anker, which was like fundamental result in that direction. LPLQ, there are some result on LPLQ of very specific multiplier like heat operator, heat like Rees kernel or such kind of by Michael Colling and collaborators. But for general Fourier multiplier, I think there is still not so many results. So maybe this kind of result is applicable. Maybe. So I work on this kind of.
Well, thank you. And thanks again for the presentation.
Thank you.
Then it's our the turn of our final speaker in this short poster session, namely Duan Cardona, also from Ghent University, who's a PhD student of Michael.
Okay, thank you very much. This short talk concerns with the global theory of subelliptic differential operators on non-commutative compactly groups.
Excuse me, your voice is producing some echo. I don't know. It's double because of double computer. I don't know why. I'm sorry for interrupting, but
yes,
no?
Yes, it's better now.
Okay, thank you. This talk is based in the reference one that you can find in this poster that I summarize here for the conference. In this reference one, we introduce a global theory of subelliptic differential operators in extensive work with 150 pages. Let me explain every part of this poster in a brief way as follows. The idea is to choose a compactly group G and as a Riemannian structure for G. So we consider as a Laplacian L associated to a Hormander system of vector fields. And we define, based in the spectral properties of L, as differential calculus. Let me recall that the theory of differential operators, born in the 70s with the microlocal revolution, summarized in the known book of Lars Hormander, the analysis of partial differential operators. These operators are used to study the global solvability for differential problems, to understand the mapping properties of certain singular integral operators, to understand the propagation of singularities in theory of distributions, and also to compute some geometric invariants arising in that theory. That is the case of the Hirzebruch signature theorem and also in the Riemann-Roch theorem. Here, we develop a global theory of subelliptic differential operators using both the representation theory of a compactly group and the global Fourier analysis on every compactly group. Quickly, compactly groups G are closed manifolds with a structure of topological group, which is compatible with the smooth structure of G. Examples are the torus, like we know, SU2, which is diffeomorphic with the sphere in R4, etc. To show our main results, let me describe the Fourier analysis on a company group quickly. Here we have a company group G, G hat, denotes the unitary dual of G, which is the set of all equivalent classes of unitary, irreducible, and continuous representation of G. And the Fourier transform of one L1 function f, defined at C, is given by this integral formula, where C is one representation of G. The idea behind in the global theory of differential operator is to associate to every continuous linear operator on C infinity G a global symbol defined in the phase space J cross G hat. And the spirit in the differential theory is to study the mapping properties of other properties, spectral property of one operator in terms of the property of the symbol. Then, for example, if we want to measure one symbol A and his derivatives as in difference, discrete derivatives in the second variable, here is discrete, with respect to the spectrum of the Laplacian, then we obtain an elliptic calculus. This elliptic calculus was developed in the book, this book that we can see here, Differential Operators and Symmetries by Professors Michael Ruchansky and Billy Turunen. But here we measure, for example, this symbol with respect to this symbol and his derivatives, and their derivatives with respect to the spectrum of the that we obtain a subelliptic calculus. That is the calculus that we developed in the reference before. Our main results in this reference is the following. We obtain a subelliptic calculus, which is closed under composition, inverse parametrices, and complex powers. We have very good boundedness properties. Then Q is the Hausdorff dimension of G associated to the control distance for the sublaplacian. And here we want to check operators associated to this class. This class here is one subelliptic class of order M associated to one sublaplacian L of the rho delta kind. This is bounded in LP. If this order M satisfies this inequality, this is one analogy of Pfefferman estimates. We also have the Calderon-Vaillancourt theorem. Operators of order 0 with these rho and delta conditions are bounded on L2. We have proved the Gardin inequality. Consequently, we have proved Will-Postness for these Cauchy problems. Using the spectral properties of this kind of operator, we have this asymptotic expansion in spectral theory. So with this kind of expansions, we can redefine subelliptic Woznicki residues. We also have a study here LP boundedness of Fourier integral operators in the setting of compactly groups with global phases and with global symbols. We study these operators also, the Dirichlet trace of these operators, like in the talk of Professor Sukochev, classification in Echardt von Neumann, consequently. And consequent of all these estimates, LP estimate, we have shared LP estimates for oscillatory Fourier multipliers, only groups. This is all. Thank you very much.
Thank you very much for this interesting presentation. Are there any questions? Yes, please, Marius.
Is there some Beers type characterization involving commutators for such a calculus, or?
Yes, the thing is that in this case, the Calderon-Zygmund kernels for the operators that we construct here are more singular than the operators associated to the Hormander calculus. Then we know that if we consider this calculus via localizations, we don't recover the calculus of Hormander. We have other kind of calculus which we apply for subelliptic problems, but it's a more singular calculus in terms of the Calderon-Zygmund theory. Then we don't have Bill's characterization in this setting, yes.
But this would be a reason not to, this is an obstacle, you cannot have it, or is it more difficult to get it?
The question is very interesting, but it's also, for me, it's open now, yes? Maybe if we consider the symbol of the Laplacian in the sense of Hormander via localizations, of the Laplacian via localizations. Maybe the Fourier multipliers of this operator are also operators in this calculus, but we develop. But is one open question for us.
Okay, thank you very much.
Thank you. Are there any further questions?